This should be a good video because in the previous few videos I've taught you a ton of information, and hopefully the individual concepts that I've talked about made sense, but really they might feel kind of scattered right now. And really I think what you probably need is some practice putting them all together, loosely speaking. So let's go through the entire process that we've learned in the previous few videos to kind of come up with a sketch, or at least an approximate sketch, of the graph of this rational function which is given to you in its factored form. I think a good place to start on questions like this is to come up with an idea of what its unfactored form would look like. So don't expand this all out because it would take you forever, but maybe you can kind of realize that from this x squared and this x cubed and this x to the first power, if I were to expand this all out, I would get 1x to the sixth power up top. That's 6 being the 1 plus the 3 plus the 2. And then I'd get a bunch of stuff that I'm not going to concern myself with because it doesn't matter for the purposes of the graph. And then I'm going to get a constant term. And to figure out the constant term, I would take this 3 and square it, this 1 and cube it, and this -4, and multiply all those together. So let's see, 3 squared is 9, 1 cubed is 1, and 9 times 1 is just 9, and 9 times -4 is -36. What I'm saying is if we took the time to expand this polynomial up in the numerator of this rational function, our leading term would be x to the sixth power, and our constant term would be -36. We can go through that same exercise for the polynomial down in the denominator. From this x and this fourth power, we would get x to the fourth, but this 8 right here makes the leading term of this polynomial 8x to the fourth. Then there's a bunch of stuff that I'm not going to concern myself with, and then there's a constant term, the constant term in this case being the -1 to the fourth power, which is +1, times the +8, which gives me +8. Now that I have the factored form of the polynomial and a rough idea of what the unfactored form of the polynomial looks like, I can figure out everything that I need for this graph. Where should we start? Let's go in the order we learn this stuff. So let's first figure out the end behavior. The idea with end behavior is you only have to look at the leading terms of your two polynomials. In this case, the term in the numerator is bigger than the term in the denominator, so this is what I referred to as case 1 in the previous videos. And what you do when you're in case 1 is you take those two terms, x to the sixth power and 8x to the fourth power, and you reduce them. I'd have 1 divided by 8, so 1/8, times x to the sixth divided by x to the fourth, so x squared. Although really I don't care so much about the numbers, what matters is that I have a positive leading coefficient and that I have an even degree. I state my end behavior by talking about what happens to the graph when I go out to the left and what happens to the graph when I go out to the right. And when I say what happens, I mean what happens to the y-coordinate. Does it go up or does it go down? Well, one way you can figure these out is because this 1/8 is a positive number, I'm going to put positive infinity right here. And because this 2 is an even number, I'm going to put the same thing here that I just wrote here. So positive infinity in this case. What I'm saying is later on when I sketch this graph, there's going to be lots of complications going on in the middle, but when I go far enough out to the left, the graph is going to go up. And when I go far enough out to the right, the graph is going to go up. So loosely speaking, it'll look like this picture. Okay, what about the y-intercept? Well, the y-intercept, much like the end behavior, is easiest to figure out if you look at the unfactored form. But instead of looking at the quotient of the leading terms, look at the quotient of the two constant terms. So my y-intercept will just be at -36/8, or I can reduce it and call it -9/2, or -4.5 if you really like decimals. I got this y-axis going through the middle of my graph, and the graph is going to cross that axis at a height of -4.5. Maybe in my picture, I can put it in right here. All right, I got the end behavior, I got the y-intercept. What's left? What's left are the things that are kind of like x-intercepts. Remember, we have 3 different cases. We're looking for numbers that make the top 0, but do not make the bottom 0. We're looking for numbers that make both the top and the bottom 0. And then we're looking for numbers that make the bottom 0, but do not make the top 0. Maybe we'll start with numbers that make the top and bottom 0. It might help to think about it as the 0/0 case. Those are what are called wholes. In this case, there are no wholes. Why are there no wholes? Because there's no number that can make both the top and the bottom of this rational function equal to 0 at the same time. Why is there no number that can make both the top and the bottom equal to 0? Because there's no factors that appear in both the top and the bottom. So in this specific example, there's no wholes. Okay, what about x-intercepts? X-intercepts come from the factors that make the top 0 but do not make the bottom 0. So in this case, I have x-intercepts at -3, -1, and +4. for this factor of x plus 3, this factor of x plus 1, and this factor of x minus 4, respectively. So on my graph, over here at negative 3, I'm going to have an x-intercept. Over here at negative 1, I'm going to have an x-intercept. And over here at positive 4, I'm going to have an x-intercept. Because the multiplicities of those x-intercepts will be important, I'm going to make note of them on my graph. This negative 3 came from this x plus 3. This x plus 3 is squared, so the multiplicity of this x-intercept is 2. This negative 1 came from this x plus 1, which is raised up to the third power, so the multiplicity of this root is 3. And then finally, this 4, which corresponds with this 4, came from this factor of x minus 4, and it's raised to the first power, so therefore its multiplicity is just 1. All that's left to do is consider the vertical asymptotes. Vertical asymptotes come from values of x that make the denominator equal 0, but don't make the numerator equal to 0. In this case, there's only one at 1, because when x equals 1, this factor equals 0, but it doesn't make any of these factors equal to 0. So the only vertical asymptote I have is at 1. You might wonder about this 8 right here, but this 8 is never going to be equal to 0 because there's no x with it. It never changes. It's always 8. It's never 0. You can ignore it for the cases of holes, x-intercepts, and vertical asymptotes. This vertical asymptote at 1 came from this factor of x minus 1, and note that it's raised to the fourth power. So this vertical asymptote that I'm about to draw right here has a multiplicity of 4. I'll write that 4 up here, even though it doesn't really matter that it's 4. All that matters is that it's even, so that when I graph this thing, I want to have the same behavior on either side of it. Recall from our end behavior that the graph goes up when we go to the left, and it goes up when we go to the right. So I can kind of toss those arrows in there, and I can connect the different dots. I typically start on the left, but you could start anywhere you want. The first important piece of information is I'm going to hit this x-intercept right here. Because it has even multiplicity, the graph is going to bounce off right there. At some point, it's going to turn around. I don't know where, because I haven't taken a calculus class yet. And the next important thing that's going to happen is I'm going to hit this x-intercept. However, at this x-intercept, because the multiplicity is odd, I'm going to pass from the top half of the graph to the bottom half of the graph. And because it's a number greater than 1, I'm going to kind of flatten out as I pass through this x-intercept. The next thing that's going to happen is I'm going to hit my y-intercept at negative 4.5, going through this pink point. The next important piece of information is this vertical asymptote. Note that I either have to go up or down forever when I approach a vertical asymptote. And in this case, I have to go down forever, because if I were to go up forever, I would have crossed the x-axis again. And I don't have any x-intercepts between this y-intercept and this vertical asymptote, so it must go down. What about on the other side? Should I start from this top or start from the bottom? Well, because my vertical asymptote has even multiplicity, I want to have the same behavior on either side of that asymptote. So since it went down on this side, it better go down on this side. All that's left for me to do is cross through this last x-intercept and point up to finish up my graph, and I end up with this approximation of the graph of this rational function, which is close enough for our purposes. In case that didn't make sense, why don't I do it one more time? If you want, you can pause the video and work on this on your own. See if you can figure out end behavior, the y-intercept, and then the things that are like x-intercepts, namely the hole, both the x and y coordinate, the location and multiplicity of any x-intercepts, and the location and multiplicity of any vertical asymptotes. It might sound kind of overwhelming, but if we take it one step at a time, hopefully it'll be manageable. A good first step is to figure out what the unfactored form of this rational function would look like. So from this x plus 3 squared, I'd get an x squared. From this x minus 2, I'd get an x. X squared times x gives me x cubed. And that x cubed times this 2x would leave me with 2x to the fourth power as the leading term of the polynomial in the numerator. Then I have a bunch of stuff. I don't know what it is. I don't care what it is. And then I have a constant term. The constant term here is a little bit tricky. It might help to think about this 2x as 2 times x minus 0 times x plus 3 squared times x minus 2. I think this is the trick that we did when we had polynomials and there were x's like this. If you write it this way, it might be easier for you to see that the constant term of the polynomial up in the numerator is actually a 0. Because this 0 times 3 squared times negative 2 times 2 leaves me with a 0. What about down in the denominator? Well, I get x times x to the fourth, so I get x to the fifth power as my leading term. And then for my constant term, I get negative 1 to the fourth, which is positive 1, times negative 2, which is negative 2. So the unfactored form of the rational function, loosely speaking, looks like what you see in red here. Now that I have this unfactored form, I can figure out anything you want. You want n behavior? Sure. For our n behavior, the degree of the denominator is bigger than the degree of the numerator. I believe that's what we called case 2. And anytime you're in case 2 for n behavior, you got a horizontal asymptote at y equals 0. What about the y-intercept? Well, the y-intercept is just the quotient of the two constant terms. So this 0 divided by this -2, 0 divided by -2 is just 0. So my y-intercept will be right here at 0. What about the whole, the x-intercepts, and the vertical asymptote? Let's start with whole, probably the hardest of the three. For wholes, you're looking for factors that show up in the numerator and the denominator. You might notice that we have an x minus 2 in the denominator and another x minus 2 in the numerator. What that means is the x-coordinate of the whole will be at +2, the root that corresponds with those factors. To figure out the y-coordinate of the whole, what we have to do is take this rational function, cancel out the x minus 2's, and then change all the remaining x's into 2's. So I would have 2 times 2 for this 2 and this x, times 2 plus 3 squared, and then I don't have this term anymore because I canceled it out. And then down in the denominator, this term is canceled, so I got 2 minus 1 to the 4th power. What's that equal to? Well, let's see. This is 5 squared, which is 25, times 4, so I get 100 up in the numerator, and down in the denominator, 2 minus 1 is just 1, and 1 to the 4th power is just 1. So the y-coordinate of the whole is 100, and the x-coordinate of the whole is 2. Unfortunately, my graph isn't quite big enough for me to see that, so maybe I can kind of scale things and pretend the 100's way up here. And what I'll do is I'll come over here to 2 and put my open circle right here at a height of 100. This open circle will represent this whole. What about the x-intercepts and the vertical asymptotes? The x-intercepts are the other numbers that make the top equal to 0 that aren't already wholes. The numbers that make the top 0 but do not make the bottom 0. So the top would be 0 if x equaled 0, or if x equals -3. Maybe it's easier to see it from this form, the x minus 0 and the x plus 3 squared. So I'm going to have an x-intercept right here. Oh, that makes sense. I already knew I was going through this point for the y-intercept. And over here at -3. And the multiplicities of those two x-intercepts are 1 and 2 respectively. So I can denote those multiplicities on my graph just so I don't forget to draw things correctly later on. The last thing that I have is the vertical asymptote. Vertical asymptotes are numbers that make the bottom 0 but don't make the top 0. So in this case, x equals 1. It's worth pointing out, vertical asymptotes show up on my graph as these dotted vertical lines. So I'll put 1 at x equals 1. And then I'll make note of the fact that the multiplicity of that vertical asymptote was 4 because this factor of x minus 1 is raised up to the 4th power. Now we get the step that I find kind of fun, although you might disagree, where we have to connect all the different dots. So from our n behavior, we know there's a horizontal asymptote at y equals 0. So eventually this graph is going to settle down on a height of y equals 0. But if you try to sketch this thing from left to right, it's a little bit ambiguous. Like, should I start out by going up like this and then go through this x-intercept? Or should I start out going down like this and then go through this x-intercept? We don't know. There's ways to figure it out from that point, but what I think might be easiest is, instead of drawing this thing from left to right, start at this point, because we know this point is on the graph, right? This point at 2, 100. So let's start right here and work our way to the right, and then we'll work our way to the left. As we work our way to the right, there's no important characteristics to capture. All we got to do is end up with a height approaching 0 for our horizontal asymptote. So the right side of our graph will just look like this. What about the left side? Well, the first important characteristic that we hit is this vertical asymptote. So the question becomes, do you want to go down forever or do you want to go up forever? Well, hopefully you can see that you can't go down forever, because if you were going to go down forever, you'd be crossing your x-axis, so you'd have another x-intercept in here. So therefore the graph must go up forever. I didn't leave myself a ton of room here, but maybe I can depict that vertical asymptote something like this. What about the other side of this vertical asymptote? Well, since it went up on the right side and the multiplicity is even, it must also go up on the left side. Working my way from right to left, the next important characteristic that I come across is this y-intercept, which is also an x-intercept. I got to cross through it because it's a y-intercept, and because the multiplicity is 1, I want to pass through the x-axis as opposed to bouncing off or flattening out as I pass through, and then continue my graph in this direction. At some point I turn around, I don't know where because I haven't taken a calculus class yet, and then the next thing I hit is this x-intercept at -3. Because the multiplicity is even, my graph bounces off at this point and heads back down. But it must turn around again at some point because eventually it settles in on a height of 0 because of the horizontal asymptote that I have drawn right here. An approximate sketch of this rational function is what you see pictured in green. Couple of comments here. Things got kind of wonky up top here because this y-coordinate was so big. But don't let that throw you off. All that I want you to see is it has to go through this open circle, and for this vertical asymptote, it goes up to the right and up to the left. So if it's easier to see it drawn like this, fine, draw it like that, whatever makes you happy. The other point that I want to make is a lot of people think about asymptotes as lines you can't cross. That's not quite true. Vertical asymptotes are lines that your graph can't cross. But horizontal asymptotes, there's absolutely no problem with your graph crossing over them. It happens all the time. Horizontal asymptotes just describe end behavior. So don't be surprised when you draw a graph and you see your graph passing through one of these horizontal asymptotes. That's totally fine. It's just the vertical asymptotes that it can't cross. That's all I got on graphs. Hopefully this is enough that you can do any similar examples working through these problems. It's kind of intense, but once you get the hang of it, it's actually kind of fun.